Okay, so as I mentioned, many of the fundamental molecules of life, so the fundamental molecules are those molecules in the three domains of life: the archaea, the bacteria, and the eukarya. Many of those fundamental molecules absorb very strongly exactly around this peak in the UVC region. And as I mentioned, this peak is important because the photons that are in this peak have enough energy in each individual photon to destroy or remake carbon covalent bonds. But they don't have enough energy to ionize. So you can't go destroying the molecule because you don't have photons of enough energy, which would be lower than about 210 nanometers in wavelength, to destroy the molecules. So this is like a very sweet spot, un área dulce para la formación de estos pigmentos. Entonces la pregunta es, the question is, could these be dissipative structures? Could each one of these fundamental molecules, these which are listed here above, could each one of these be a dissipative structure and formed that way, just like a hurricane is formed over a heat gradient or temperature gradient? So before describing the microscopic dissipative structuring of these fundamental molecules, let me first describe what is dissipative structuring in general for microscopic structures. So in nature, there are two classes of structures: equilibrium structures, which are obtained through the minimization of a Gibbs potential or some thermodynamic potential. The Gibbs potential is at constant temperature and pressure. So that gives rise, the minimization gives rise to these crystalline structures, or for example, the solar system with the gravitational potential. Now there's another class of structures in nature, which are called non-equilibrium structures. And these arise through the optimization of dissipation. So the examples are the hurricanes, which is dissipating temperature gradient from the hot ocean surface and the cold upper atmosphere, and the Bernard cells, which are convection cells, which are also dissipating a heat gradient. And we also have a Belousov-Zhabotinsky reactor system is an example of non-equilibrium dissipative structures, which is dissipating a chemical potential, which comes in with the reactants into the system. They react, produce product molecules, and then the products are exposed to the environment. So there's a chemical potential over the system, and this system is dissipating that chemical potential, just like the system dissipates the thermodynamic, the heat or the temperature gradient potential. And in this case, in fact, we're breaking symmetry not only in space, but also in time, because these figures can be changing with time. We have a constant flow of reactants into the system and a constant output of the products. Now, the conjecture is that the molecules, the fundamental molecules of life, were also dissipative structures, but in the UVC. So DNA and the amino acids, fatty acids were all microscopic dissipative structures. But before describing a given example for microscopic dissipative structuring, let me first remind you about macroscopic dissipative structures. And the example I'll give is the Bernard cell. And this is structuring over coordinate degrees of freedom. Okay, so we're structuring over the distance dimension. So these Bernard cells consist of two plates, a hot plate, which is at the bottom, and a cold plate at the top. And between them, a liquid under the force of gravity. Now, as long as the temperature gradient, the difference in temperature between the two plates is not too great, then we get only conduction. We don't have these cells occurring. These convection cells still do not arise. We have only conduction, which is the vibrational movement of the molecules, which is transferring heat from the bottom plate to the upper plate. But as soon as we get over a critical temperature difference, okay, so we're changing now the temperature difference between the upper and lower plate. And as soon as that temperature difference is over a particular value, which depends on the Rayleigh number, okay, which depends on the force of gravity and the viscosity of the material and on the coefficient of thermal expansion and on the size of the system. And as soon as we get over that particular critical value, the Rayleigh number, then we all of a sudden get structuring these Bernard cells. We still have conduction. Conduction is still occurring, but we have now a new irreversible process, which are these Bernard cells. And this is increasing the flow of heat from the lower plate to the upper plate. So in thermodynamic theory of non-equilibrium theory, and we're going to get into this next class. So those of you, for example, Ricardo was very interested in giving more of the mathematical formulation, then please read or look at my videos about Prigozhin's book, at least up to chapter 3. And next class, we're going to get into a little bit of that. I didn't want to go into the whole formalism because I know that bores people watching the mathematics or trying to understand or being lost. Then they tend to not enjoy the talk. So I think I would prefer to give these kinds of talks and to have just a summary of the important points of non-equilibrium thermodynamics and let you guys read the book of Prigozhin and then look at my videos and try to understand. And if you don't have any, if you have problems, you bring them to class and we can discuss them in class, especially to the next week's class. I will give a summary of the basic concepts of non-equilibrium thermodynamics, and then you can ask me all the questions you want. Okay, so for this system then, we go from conduction to convection plus conduction. And in this regime, we're in the nonlinear regime, nonlinear between the flows and the forces. So here the flow is the flow of heat, and the force is the gradient of the temperature. So we can write the entropy production per unit volume. It's just flow times the force. This we'll see from Prigozhin's book. So that corresponds to the flow of heat and minus the gradient of 1 over the temperature. It's really 1 over T1 minus 1 over T2 in the case of a discrete system. But in the continuous system, it's the gradient of the temperature. So this is the nonlinear regime between flows and forces when we have this structure. And in fact, in this nonlinear regime, we actually have two solutions, or what we call stationary states. And these solutions correspond to the hot liquid coming up in the center, cooling off on the top, and then going down around the edges. That's one solution. And that has one value for the entropy production, which we plot here. So this is the point at which we all of a sudden get these two solutions. So this is when we go above the Rayleigh number, this critical Rayleigh number, and we get bifurcation, and we get two solutions because it's a nonlinear problem. And one of them is with the hot liquid coming up in the center. But the hot liquid could also come up around the edges. That's another solution. You cool off on the top and go down in the center. That's another solution, but it's extremely rare. It's not very probable. And in fact, if you calculate the entropy production, it's less. So this is the other solution with less entropy production. Now, nature seems to take the direction of increasing entropy production. And we'll see that that basically happens in the case when we have non-linear positive feedback, or for example, autocatalytic reactions, if we're talking about chemical reactions. This is the flow of heat, but also we could have flow of chemical reactions, or the rate of chemical reactions. And when we go into this nonlinear regime, then we have these two or more solutions to the problem. Okay, so that's dissipative structuring for macroscopic systems. Now, dissipative structuring for microscopic systems, like for example, the production of adenine, which is one of the bases of DNA. And as I mentioned, it was a UVC pigment at the beginning of life. So this microscopic dissipative structuring is over molecular degrees of freedom. And they are UV induced. They're induced by this UV light. UV light gives us access to these new degrees of freedom. And these are, for example, for molecules, the isomerizations, tautomerizations, rotations around double bonds or single bonds, charge transfer, substitutions, exciplex formation, and whatever molecular reconfiguration of the system, which we can do with ultraviolet light, they are considered microscopic degrees of freedom. Now, it can be shown that you can produce adenine, one of the bases, rather easily with just hydrogen cyanide in water and with ultraviolet light over the system. And this experiment was done in 1966 by Ferris and Orgel. And later, Boulanger et al. Did the quantum mechanical determination of the potential energy surface of the excited and ground state. And they were able to look at the energy barriers in going from one molecule to another to arrive finally at adenine. So this is the reaction, chemical reaction and photochemical reactions occurring here. And I'll just describe a little bit, not in too much detail, of what is happening. So we start with 4 molecules of hydrogen cyanide. And through a chemical reaction, this is basically just minimizing Gibbs free energy, we get to cis-DAM, okay, which is this structure. So this is the lowest energy solution for 4 molecules of hydrogen cyanide. And this has nothing to do with non-equilibrium. This would happen in any system, even if the light wasn't incident over the system. But now to go to the second stage here, which is called trans-DAM, you can see that that's just a rotation around this double bond here. So we have a rotation of this 180 degrees around the double bond to give us this structure. And that turns out to have a large activation energy. We need to put a lot of energy in the system because this is a double bond. The double bonds are very strong bonds. So to get enough energy to go over the barrier, we have to absorb a photon. And this is a photon at 298 nanometers. Now, if we look on the graph of the light, which is coming into Earth's surface at the origin of life, we had very little light at 298 nanometers here. But we still had some, so it could occur, but with low frequency. And it also goes up in energy. We have this is a little bit higher Gibbs free energy. Not much, but it's a little bit higher. But it has a very large activation barrier, so we have to absorb a photon to go there. And then in the second step, here we go from trans-DAM to AIAC. And that occurs just by a proton transfer here from this group to this nitrogen group. Okay, so that gives us this configuration. And for that, we also need to absorb a photon at 313 nanometers. So we're here on the graph of the light coming into Earth at the origin of light, where there's a little bit more light. And to form the ring formation here, we need to absorb another photon at 275. So we're about here. Okay, now there's more light. And then as we go on, we get to AICN, which is absorbing at 250. So that's 7 here. Okay. And then with the addition of another hydrogen cyanide molecule, we form adenine. And that's absorbing at 260 nanometers, exactly where there's a peak in the spectrum, which is arriving at Earth's surface during the Archean, during the origin of life. Now, the interesting thing is we go from one molecule to another and we look at its photon absorption cross-section. We find that the photon absorption cross-section is gradually increasing. So if you want, you can look at this like a little hurricane, which is starting very small and it's gradually increasing into a category 5 hurricane, where it's dissipating the greatest of the temperature gradient difference over the ocean and the upper atmosphere. Here we're absorbing stronger, so we're dissipating more and more photons as we go from one intermediate molecule to the next one. So this has a very large molar extinction coefficient. And not only that, but it's very rapid in dissipating its electron excitation energy induced by the photon. So when the photon comes in on this adenine molecule, it causes the electrons, which are here, which are they're shared by the different nuclei here. So there's like a pi formation. They go to a collective electron excitation. And we can go very rapidly to the ground state just by deformation of the molecule. So this proton here, I don't find my marker, here it is, this proton, this carbon atom here, sorry, and hydrogen, this proton with the carbon atom, comes out of the plane when it's excited, when it absorbs the photon. And that gives us a different vibrational spectrum, which is different from the ground state spectrum, which is corresponds to a planar molecule. So we have different vibrational states superimposed on the electronic excited state. And in fact, they become at some point degenerate in energy. So the energy can go from the electronic excited state directly to the ground state through vibrational motion of the molecule. And it goes back to its planar state. That happens very fast, on the order of 10 to the minus 12 seconds. So these molecules, these fundamental molecules, are very efficient at absorbing and dissipating into heat the photon excitation energy induced by the photon, 10 to the minus 12 seconds. So then RNA and DNA are excellent dissipative structures. They absorb one photon, they convert it into about 30 or 40, depending on the energy of the instant photon, in about 10 to the minus 12 seconds. And that's what a hurricane is doing. It's absorbing photons in the infrared from the ocean surface at a high temperature, and then emitting them into many more photons in the infrared at a lower temperature of minus 15 degrees centigrade. And I think the ocean water has to be over like 28 degrees centigrade before you can get a hurricane. Okay, so this is macroscopic dissipative structuring, the hurricane, and the production of these molecules is microscopic dissipative structure, but it's basically the same thing. So I've given you the case for adenine, but we're doing it now for guanine. In fact, Claudette, my student, who is with us today, is doing it for guanine. We have it almost ready, I think. And then we can do it also for cytosine and thymine. So this gives us the dissipative structuring of all of the molecules inside the DNA structure. Of course, these molecules, these bases, nucleobases, they're connected with sugar groups, ribose, and also with phosphate groups to make the backbone. I won't go into that, but you can find that in my book. I give a description of how that is also done under ultraviolet light. And they have, in fact, verified with experiments that occurs. Okay, so this was the first component of the thermodynamic dissipation theory of the origin of life, is dissipative structuring. Now let me go to dissipative proliferation. So this is the case in which we find an increase in the spread of these molecules, or a DNA, the proliferation of DNA. I'm going to give the example of DNA right now, over the whole surface of Earth. And it has to be enzymeless, because you know today that to denature and later extend DNA, that means make a copy or replicate DNA, we need about 20 or 30 different enzymes. And these enzymes are very complex proteins which could not have existed at the origin of life. So we need a physical basis to describe this replication. And so we have come up with this ultraviolet and temperature assisted replication, which we call UV TARP. So if you remember, I said that the ocean surface at the origin of life were about 85 degrees centigrade. And they were cooling throughout the Archean. The surface was cooling. So you can imagine if you did have these molecules and they did form single strands of DNA, that the single strands would find a complementary double strand. And then it would be stuck in this configuration. And if the surface temperature of the oceans didn't increase, it would stay at this double configuration, so it couldn't replicate. Because the first step you need in replication is denaturing. But if you can imagine, in the afternoon, the ocean surface would have been warmer, maybe about 3 or 4 degrees centigrade warmer. And we're also absorbing ultraviolet light on these bases. And so this heat or the dissipation of these photons into heat can also cause the denaturing of DNA, even though the surface temperature is below their denaturing temperature. I should say this is a very interesting value for the temperature that they have found with these oxygen isotope ratios of about 85 degrees centigrade, because this corresponds in fact to the denaturing temperature of short strand and intermediate strand DNA. So that's very interesting. The life started when the surface temperature was denaturing temperature of DNA. Okay, and that fits with this UV tar mechanism. So as the temperature was decreasing of the ocean surface in the day, it would warm up because of the infrared light from the sun, and also because of the absorption and dissipation of the ultraviolet light. And also another factor is that when we denature DNA from double strand to single strand, it starts absorbing more. It absorbs about 30% more than in double strand. This effect is called hyperchromism. So we get more absorption, so there'll be less chance that these two go back together again to form double strand. And so they would start to separate on the ocean surface. And then at night, when the ocean surface cooled, then we could have these strands finding their complementary base pair, okay, the pair which corresponds, for example, adenine corresponds to thymine, guanine to cytosine for DNA. And then we could form the complementary strand of the single strand, and then have two double strands, where at the beginning we only had one. So that's replication. Okay, so the interesting thing about this is that it's template directed. So this single strand acts as a template for locating and fixing its complementary bases to form the double strand. And therefore, because it's template directed, it's autocatalytic. So this consisting of one strand here, forming a second strand, means that it's autocatalytic. As you remember, I said in the cases of autocatalytic reactions or mechanisms, you can have this positive feedback effect, which can allow you to select configurations which correspond to greater production of entropy later in step 3. I'll talk more about that. But anyway, replication here is tied to photon dissipation or entropy production. And that's the important thing, that any irreversible process or any dynamics like replication has to be tied to some kind of dissipation of some generalized thermodynamic potential, whether it's a heat gradient, a photon gradient, or a chemical potential. It has to be tied to dissipation. And that's what most of the people who have been working in the origin of life have been ignoring, that life is not just a collection of fundamental molecules. It's really a dynamic process. And to describe the dynamics, you have to talk about dissipation. You're not going to get dynamics without dissipation. The system will just go to an equilibrium state and stop. And that is death, actually. Okay, so we did this experiment. So this was the theory, no? And then we did the experiment. We have UVC light giving us light in the UVC range of 210 to 290 nanometers. And we have in this little black box, we have the DNA inside a solution of a buffer solution, water, with some phosphates, buffers, to keep the pH constant. And then we have a spectrometer at the bottom, which is measuring the absorption of this UVC light in the DNA. And we have also another spectrometer which measures the dispersion or the scattering, which is in fact very small. We didn't actually even use this data because we couldn't even make sense of it. It was too small. And this is connected to a temperature controller, so we can control the temperature of the solution with DNA. And we have a water supply which just allows us to input or remove heat very quickly from the system using this water stabilizer. Just a pump which it's like a radiator which runs water through to keep everything at a fixed temperature. the temperature that we decide with this controller, which is later connected with the computer. Okay, so this is the absorption spectrum of DNA. This is 25 base pair DNA, which we had produced in the Institute of Physiology in the UNAM. And we can make any DNA we like. We can invent the sequence and just ask them to produce this sequence, double-strand DNA for us. And they did that. And then this is the result of the absorption as a function of wavelength. Now here, look where it's absorbing. It's absorbing exactly at 260 nanometers. And if you remember, the spectrum of light at Earth's surface peaked at around 260 nanometers. And in fact, it looks very similar to this. In fact, I have a slide in which I show the absorption of DNA and the light coming into Earth, and it looks almost a perfect fit. So we did this at different temperatures, now starting from 30 to 80 degrees. And you know that you can denature DNA by increasing the temperature. When we get to 80 degrees, this short strand DNA denatures. And this is just the contribution around these temperatures in a 3-degree bin, but don't worry about this, we're not going to get into that. Okay. So this is temperature-induced denaturing. And we're realizing that because we see this hyperchromic effect. When we go from double-strand to single-strand DNA, we increase the absorption, 260 nanometers. So what about light-induced denaturing? So this is the case for salmon sperm DNA. We brought the system up to a constant temperature of 40 degrees centigrade, and we kept it constant, that temperature. And with the light on, we allowed the system to come to an equilibrium. It's an equilibrium between single-strand and double-strand DNA. And then we turned the light off and waited about half an hour, and then turned the light on again. So the down arrows here, the arrows, which are pointing downward, corresponding to turning the light off, and the up arrows turning the light on. And you can see that whenever we turn the light on, we would go up in absorption, extinction. This is really absorption here. So what's happening is we're going from single strand to double strand, this hyperchromic effect, increasing the absorption as we go from double strand to single strand. Then when we turn the light off again, then we get renaturing. So the system goes back to double strand, so we get less absorption. Then off and on and off and on. So we repeat this, we see that we are causing denaturing by this UVC light. And that's the first step in replication. That's what we wanted to show, that we could get replication using only the physical mechanisms which were available at Earth's surface. Okay, and we did that also for 25 base pair DNA and plotted it as a function of wavelength. So here again, we see that we are getting an increase, because this is the difference between at the end of the light on spectrum, subtracting the spectrum at the beginning of the light on period. So this gives us the difference, which shows that there is more absorption. And obviously there is more absorption because it goes up here, absorption, extinction, and as a function of wavelength. And this is for the double strand DNA, the solid lines, at different temperatures, different fixed temperatures, okay? And this is for single strand. This was as a control to see that we didn't have something which was not denaturing, which was confounding us. So it was a control to use single strand, because single strand obviously cannot denature. And we found for single strand, in fact, we get lower absorption at about 270 nanometers here. And that is because we're forming pyrimidine dimers. We'll get into that in another talk. But it's just when you have two bases, like for example, two thymines together, then a photon can come in and it forms a covalent bonding, and that reduces the absorption in the future. So we get a decrease in absorption for single strand. It's also occurring for double strand, but we don't see it because we get much more denaturing, which increases the absorption. And if we plot that as a function of temperature, we get light-induced denaturing as a function of temperature. And as you see, as we get close to the denaturing temperature, we get a very large increase. So this is effective UVC denaturing rate in percent per hour, which increases from like 1% to all the way up to 24% here at 70 degrees centigrade. So what's happening then is we have a photon coming in, it's being absorbed on a particular base, or maybe two bases, and that's causing deposition of energy, which causing system to denature, and that increases the absorption. And we can continue this throughout the day or the afternoon until we get denaturing and the two fragments, they separate. And then at night, when the temperature cools, we can get extension or the formation of a second complementary strand to the initial strand. And this extension has been already shown experimentally. So we don't have to show that here, don't have to prove that. So now I'll just go rather quickly because we have only about 7 minutes left to the other step, which is the other component of the thermodynamic dissipation theory of the origin of life, which is dissipative selection. And for here, we have to get into a bit of the thermodynamics of Prigogine, classical irreversible thermodynamics, developed by Onsager and Prigogine. And this is for what they won the Nobel Prize for. And this will allow us to include evolution in our system, in our thermodynamic system. So just very briefly then, the production of entropy, P over T, this production of entropy per unit volume, V, sigma is per unit volume, sometimes written as DIS by dt, which this refers to internal production of entropy in the system. Okay, is just equal to a bilinear form of forces times flows. So for example, in the case of a chemical reaction, the force is the affinity over the temperature, and the flow is the rate of the reaction. So that comes from the book of Prigogine. We're going to see that later in the class. We're going to go over that. And for every different irreversible process, the different forces and flows. For example, in the case of the flow of heat, that's J is the flow of heat, and X is the force, which is the gradient of 1 over the temperature. And the fact that we can write it as bilinear form of X times J means that we can describe this as in two parts, divide the change in the production of entropy in two parts, one due to the changes in the forces, and the other one due to the changes in the flows. Now, the most universal result, or most general result of Prigogine is what's known as the universal evolutionary criterion, that this part always has to be negative definite. And this is sometimes known as the Glanzstorf-Prigogine criterion. Don't worry about this now. We'll also derive that in class later. But this part has to be negative definite. But it doesn't say anything. There's nothing you can say about this part, about the flows. Do the flows increase or they decrease? If they increase, then we're going to get an increase in the production of entropy because it goes as the flows times the force. If they decrease, then we'll get a decrease. So in fact, the rate of the production of entropy can go either up or down. It depends on the system. But if we have an autocatalytic system, for example, we have autocatalytic chemical reactions or photochemical reactions, then the tendency is for this to increase, and it increases over this decrease. So we get a general tendency of this to increase. The rate of the production of entropy increases. And that's what I mentioned here in this bifurcation diagram. If you remember, no, we go generally up, but sometimes, because it depends on the fluctuation, sometimes the production of entropy can go down. Okay, but generally we're going up. And so this is evolution. The system is evolving over these different stationary states which are available to this nonlinear system. And each of these states has different entropy production, and the tendency of nature for these autocatalytic or positive feedback systems is to increase the dissipation as we evolve over time. Okay. So to give an example, this is the example of dissipative selection of adenine, going back to this chemical and photochemical reaction system. So here we have 7 different reactions occurring, but there are in fact many more reactions because we have to take into account those reactions which are also competing with these reactions. And so, in fact, we have about 16 reactions or 4 chemical reactions, which are important for the system. So we programmed them all. So this is, for example, hydrogen cyanide going to formamide, which is hydrolysis. So this is one of the reactions which is not included here, but it's a competition for hydrogen cyanide. So we have to include it. So this is a chemical reaction. We have a rate constant. And we also have photochemical reactions, this converting formamide into formamidic acid through the absorption of a photon. Or for example, this case where we're going from cis-dem to trans-dem, that is this equation here, absorbing a photon at 298 nanometers. We go from cis-dem to trans-dem. And for these photochemical reactions, we have a quantum efficiency. So therefore, the model is that we have this spherical vesicle, okay, which is subjected to ultraviolet light floating on the ocean surface, and which is permeable to water and hydrogen cyanide. And we look at the system over 10 days. And we evolved these equations for 10 days, day and night. Each day was 16 hours, so 8 hours of sunlight and 8 hours of darkness. And we include a perturbation because this system is nonlinear. In fact, this trans-dem acts as a catalyst for the formation of cis-dem from 4 molecules of hydrogen cyanide. So this is acting T here, and this equation is acting like a catalyst. So these are nonlinear equations, differential equations. So, so therefore we can have more than one stationary state. And the idea of the perturbation is to see if we go from one stationary state to a new stationary state, if we can increase the entropy production there. So this is the set of equations, which I won't go into detail, but they include the fusion and these chemical reactions and these photochemical reactions. And we have to solve these. These are the different concentrations of these intermediate molecules here. These are the intermediate molecules. These are their concentrations as a function of time. And when we do that, these are the graphs we get. And this is for adenine, which is the important one. And then you see when we have the perturbation, we all of a sudden get a very large increase in the production of adenine, and therefore also in the dissipation, because as we mentioned earlier, adenine is the best molecule of the intermediate molecules for absorbing and dissipating photons. So, and these other lines here, different colors, are the different molecules, intermediate molecules as a function of time. So over 30 days, we get an increase of about 5 orders of magnitude in the concentration of adenine through this reaction diffusion system. If we look at the entropy production due to the formation of these molecules, which are absorbing photons and dissipating them into heat, and then we see that also at 10 days, when we do the perturbation, we get all of a sudden an increase in the entropy production. So we get an increase in the system, in the production of entropy in the system. And that is evolution. That's due to the nonlinear nature of the